Hi, my name is Oscar, and I'm going to present some joint work in coding theory with Francisco Pernice and Mary Wootters, where we showed that list decoding capacity implies capacity on the symmetric channel. So first, let me start with some coding theory definitions. A code is just any subset of fq to the n, and a linear code is a subspace of fq to the n. Now we want to think of a code C as the set of all possible messages that two parties might want to send to one another. And the idea is that when the sender picks one of these messages, little c, which we'll call a code word, and sends it to the receiver, along the way there is going to be some errors. And so the receiver will see a corrupted version of the sent message, and the goal is for the receiver to still be able to figure out what that sent message was, despite the presence of these added errors. Now, we will consider two different models for these errors, and they're the main models that are standard in coding theory. The first one is a stochastic model, where in each coordinate, independently with probability p, the symbol that is in that coordinate will be changed to a uniformly random different symbol in fq. And then the other model is the adversarial model, where an adversary is allowed to come in and corrupt up to pn coordinates. And your adversary gets to both pick the location of those coordinates and also the actual symbol that they put in. Now, when we design codes, we want them to have two main properties. So the first property is we want the dimension of the code to be as large as possible, because the more messages you have, the more information the two parties can transmit to each other. And then the second property is we want the code to be able to be resilient to as many errors as possible. Now, in the random error model, the optimal trade-off between these two properties is well understood. So Shannon showed in the 1940s that there are codes of dimension 1 minus h of p times n that can decode p random errors with high probability, where here hq of p is the q-ary entropy function. And this trade-off is optimal in the sense that if you have a linear code of dimension larger than 1 minus h of p times n, then with high probability it will not be able to decode p random errors. On the other hand, for adversarial errors, it's reasonably easy to see that if you want your code to be able to recover from pn adversarial errors, then you need the minimum distance to be at least 2p times n, where the minimum distance is just the minimum Hamming distance between any two code words in your code. The reason for this is pretty simple. It's just that if you have two code words c and c prime that are separated by less than 2pn, then there's a point x in the middle here for which the adversary can corrupt c to x by only using pn coordinates, and can also corrupt c prime to x by using only pn coordinates. So that means that if the receiver receives the message x, they won't know if the sent message had been c or c prime, and so they won't be able to recover the sent message. Now, one consequence of this fact that the minimum distance needs to be at least 2pn is what's called a singleton bound, which says that any code C that can recover from pn adversarial errors needs to have dimension at most 1 minus 2p times n. And for comparison, with the random error case, like when q tends to infinity, so for very large alphabets, the best you can do for random errors is 1 minus p, because this function, this q-ary entropy hq of p, tends to p as q goes to infinity. So at least for very large alphabets, you can recover twice as many random errors as you can adversarial errors. Now, there's another notion of decoding called list decoding. And in list decoding, the setup is the same. So the sender chooses some code with C and sends it to the receiver. And then along the way, there's some errors. Those errors can be random, they can be adversarial. But the point is the receiver sees a corrupted version of the sent code word. But now the difference is, instead of outputting one code word, the receiver is asked to output a list of L potential code words, where L is a predetermined list size. And we see that the receiver successfully decoded the message if the sent code word C is in the list of L code words that the receiver outputted. Now, this framework has been studied extensively as well, and Elias showed that as long as your list size is super constant, then there will be codes of dimension 1 minus h of p times n that can list decode pn adversarial errors with list size L. And hopefully, this expression rings a bell because it's exactly the same as what we had for random errors. Okay? And so the point is the optimal trade-off between the dimension of a code and the number of errors that the code can tolerate is the same if you're trying to uniquely decode random errors or list decode adversarial errors. And one natural question to ask then is this a coincidence, or is there a formal relationship between these two frameworks? And that's what we show in our main result. So we show that it's not a coincidence. There's a relationship at least in one direction. So if C is a linear code that achieves list decoding capacity for adversarial errors, meaning it has the optimal trade-off between its dimension and the number of adversarial errors that it's able to list decode for. So if you take such a linear code C and it has super constant minimum distance, then C will also achieve capacity on the symmetric channel, meaning it will have the optimal trade-off between its dimension and the number of random errors that it can tolerate for unique decoding. Now, one consequence of our result is that we get new capacity achieving codes for random errors, because there were some codes that were previously known to achieve list decoding capacity, but they were not known to achieve capacity for random errors. So for example, algebraic geometry codes and multiplicity codes, both of these, because of these previous papers, were known to achieve list decoding capacity. And so by our theorem 1, they also achieve capacity over the symmetric channel. Now, in terms of proving theorem 1, theorem 1 actually follows from our theorem 2 here, which says that if you take any linear code C that has super constant minimum distance, then the probability of a decoding success for C will transition very sharply between 1 and 0. Meaning that if I vary P, so if I look at random errors of probability P, at first when P is close to 0, the code will be able to decode any sent message with probability very close to 1. And then as I increase P, at first it'll stay very close to 1, and then suddenly there will be a very sharp drop off to 0. Okay, so this is what this theorem is saying. As you vary the probability P of an error, the decoding error of any code with large minimum distance will transition quickly from 1 to 0. Now, this theorem was proven for Q equals 2 by Tillich and Seymour in like 25 years ago. And then we generalized it to arbitrary Q in this paper. So first, I'm going to sketch you the proof of why theorem 2 implies theorem 1. And then I'll discuss a little bit the ingredients of the proof for theorem 2. So let's prove that theorem 2 implies theorem 1. Now, theorem 2 was the statement that if you take any linear code C with super constant minimum distance, then its probability of a decoding success will have a sharp transition. And what we'll want to show for theorem 1 is that as long as C can list decode Pn adversarial errors with a list of size L that's not too large, and I'll make it clear in a bit what I mean by not too large, then C can also uniquely decode random errors of probability around P, so P minus little o. And our first step towards proving this will be to show that when the errors have probability P minus 1 over n to the 1/4, then our success probability is at least around 1 over L. And the reason for that is pretty simple. It's just that when you have errors of this probability, but a turnoff bound, it's very unlikely that we'll have more than Pn errors in total. But we know that if you have fewer than Pn errors, then there's at most L potential code words that the receiver could confuse the sent code word for. And so if you want to have a probability that's about 1 over L, all you need to do is, as the receiver is find the L code words that are the closest to your received message and output one of them uniformly at random. Okay, so what we've proven is that there is some p minus little o of 1 for which our success probability is at least 1 over L. And now what we'll want to do, of course, is just apply theorem 2, which was that the success probability has a sharp transition. So as long as 1 over L is not too small, then the sharp transition is going to kick in, and so I'll be able to reduce the error rate by just a little bit and boost my success probability all the way to 1 minus little o of 1. And it turns out that the cutoff for this sharp threshold is around 2 to the minus square root of the minimum distance. Okay, so as long as 1 over L is smaller than that, then the whole argument will work, meaning that if your code C can list decode Pn errors with a list of size L that's at most around 2 to the square root of the minimum distance, then your code will also be able to uniquely decode random errors with probability around P. Okay, great. So now we've proven that theorem 2 implies theorem 1. And so what's left to show is theorem 2. Okay, so we want to show that the probability of decoding success has a sharp transition. So let me define f of p to be the probability of a decoding success when I have random errors of probability p. And we want to show that the curve looks like what's on the left here, the green curve on the left. And formally, what we'll try and show is that the derivative of f of p has this form. So it can be bounded by minus f times 1 minus f times something that's super constant. Okay. Now I'll explain in a little bit why this is enough, like why this implies a sharp threshold. But first, let me note that this is not like a new idea. We didn't come up with this. It's been used in many, many papers before us. And as far as I know, it's the most well-known and the most successful approach for proving sharp transitions in general. Not just in coding theory, but just if you want to prove that some phenomenon has a sharp transition, one very good idea is to try and prove that the derivative of your function behaves like this. Okay, so let me explain why an inequality like the one that we have here implies that you have a sharp transition. So first, note that we're proving that the derivative is negative, which is good, right? We want to show that our function is decreasing. And then also the point is just as long as the function f of p is close to 1, then this term can force this derivative to be close to 0. So the derivative is allowed to stay close to 0 as long as f is close to 1, and so the function is allowed to be flat as long as f is close to 1. But as soon as f goes like a little bit away from 1, so let's say it's like a very small constant away from 1, now suddenly this 1 minus f times f is a constant, and so this super constant term here is going to kick in. It's going to make the derivative like a very large negative quantity, meaning that your function will drop very quickly. And your function will keep dropping until you reach a point where f of p is very small, and then because of this term here, it will allow the derivative to go back to being close to 0, and so the function can flatten out again. Okay, so basically the idea is just if your function is not very close to 1 or very close to 0, f of p times 1 minus f of p is going to be a constant, and so this omega of 1 term will force your function to drop very quickly. Okay, so this is our new goal. As long as we can prove an inequality like this for this specific function f of p, then we'll have shown theorem 2, and as we've seen, theorem 2 implies theorem 1. Now, in order to prove the inequality that we saw on the last slide, we'll first need to do a little detour and talk about derivatives of monotone functions. So we say that a Boolean function f is monotone decreasing if for every point x and every coordinate I, we have that f of x where I set the ith coordinate to be 0, is always greater than or equal to f of x, where I set this ith coordinate to be any other value in fq. And for any monotone function f, we'll be interested in its boundary function hf. Now, what is this function hf? Well, let's say that we have some function f that evaluates to 0 on the black dots and to 1 on the red dots. First, when f of x is equal to 0, hf is also equal to 0. So on all the black dots, hf evaluates to 0. And then on the red dots, on the dots where f of x is equal to 1, what the boundary function does is it looks at all the neighbors and it counts the number of coordinates along which you can move and find some point x prime that has f of x prime is equal to 0. So in this case, there are two such coordinates. I can move along this axis and find a point that evaluates to 0, and I can also move along this axis and find a point that evaluates to 0. So hf of x here is equal to 2. And why are we interested in this function hf? Well, it's because Margulis and Rousseau showed in the 1970s and 1980s that for any monotone decreasing function f, the derivative of the expectation of f can be bounded in terms of the expectation of hf. Now, I won't prove this, but I'm flashing the proof here just in case you're interested. Okay, now that we've seen all of the tools that we are going to need, I'm going to give you a general overview of how the whole proof works. So first, for any linear code C, we define fc to be the indicator function of a successful decoder. Okay, so for the rest of the talk, we're going to assume that the SAND code word is the 0 code word, and then f of x is 1 if x, which is the error string, or the string that the receiver sees, they're the same since we're sending the 0 code word. So if x is closer to 0 than any non-zero code word, then the decoding will be successful, and so fc is 1, and otherwise fc is equal to 0. And our goal will be to prove that the expectation of fc has a sharp transition, right? We showed that that would be enough to prove our theorem 1, which was that list decoding capacity implies capacity on the symmetric channel, and the idea is that you can use this sharp transition to boost your success probability from 1 over L to 1 minus little o. Alright? Now, in order to prove a sharp transition, we also saw that it's sufficient to give bounds on the derivative of the expectation of f of this form, right? The point is that the super constant term thing will mean that whenever the expectation is away from 1 and away from 0, you have a very large negative derivative, and so your function will drop quickly. And then we also saw that the left side of this inequality, by the Margulis-Rousseau lemma, can be bounded in terms of the expectation of this boundary function hf. So now there are two remaining pieces that we need to look at. So first, let me define delta g for any function g. We define delta g to be the minimum non-zero value of this neighbor function. So the first lemma that we're going to need is that for any function g, the expectation of hg can be bounded this way. Okay, this is an isoperimetric inequality. It was proven in the case q equals 2 by Talagram, and then we generalized it to arbitrary q. And then the second lemma that we're going to need is that for a specific function fc, the minimum non-zero value of the neighbor function can be bounded in terms of the minimum distance of c. And this was proven by Tillich and Zemmour in 2000, and we also generalize it to arbitrary q in this work. Now, I'll let you verify that combining these two lemmas with these expressions gives us this theorem, and that this theorem is sufficient for sharp transition. I won't be able to prove lemma 1 to you because it's fairly technical, but let me just give you a sketch of a proof for lemma 2. Remember that our function fc is the indicator function for a decoding failure, and so what our lemma 2 states is that for any error string x where the decoding would be successful, either x has no neighbors where the decoding would fail, or if it has at least one such neighbor, it must have many neighbors where the decoding will fail. So let me sketch out a proof for the case q is equal to 2. I won't show the case where q is larger than 2 because it gets a bit too technical, but suppose that q is equal to 2 and consider some linear code given on the right here. So the blue region is just the Boolean cube and the black dots are the code words of C. Without loss of generality, we're going to assume that the sender sent out the 0 code word, and this yellow region is now the set of all error strings where the decoding is successful. Right? It's the set of all strings that are closer to the 0 code word than to any other code word. So suppose that we have a point x where the boundary function hf is non-zero. Right? We want to show that if the boundary function is non-zero, then it's very large. So suppose it's non-zero, that means two things. First, it means that x must be in the region of decoding success, right? So fc of x must be 1. And second, it means that there must be a neighbor of x that is outside this region of decoding success. So this gives us two important consequences. The first consequence is x must be about halfway between 0 and c, right? Because x was closer to 0, but then by changing just one coordinate, x became closer to c. And then for the second point, let us try and understand why this neighbor became outside of the decoding region. So the point was xi here must have been 0 and ci was 1. And so when I switch xi from 0 to 1, my distance to 0 grew by 1 and my distance to c went down by 1. And that's why this new point is now closer to c than to 0. But the point is, there's nothing special about the ith coordinate. If I look at any coordinate j where xj is 0 and cj is 1, then by switching sj from 0 to 1, I will get a distance 1 further away from 0, and I will get a distance 1 closer to c. So that means that for all of the points, for all of the coordinates j where xj is 0 and cj is 1, I've obtained a neighbor of x that is outside of the decoding region. That's great, that's exactly what I wanted to show. So how many such coordinate j's are there? Well, the point is there must be at least the distance between 0 and c of them, right? Because x was about halfway between 0 and c. So that means that if you look at all the coordinates where where 0 and c disagree, so all the coordinates where cj is 1, at least half of them must have x agreeing with 0. So at least half of them must have xj is equal to 0. So we have about at least distance between 0 and c over 2 coordinates where xj is equal to 0 and cj is equal to 1. Each of those coordinates give us a neighbor of x that is outside the region of decoding success. And so we've shown that there are at least this many neighbors, which is exactly what we wanted to show. Okay, so this gives us lemma 2. And then if we go back to this overview, right, we've seen that combining lemma 2 with this lemma 1 that I didn't prove, as well as all of these other things that we've seen, gives us our final theorem. So this concludes the talk. Thank you.